Today we are going to see about the Hermite Differential Equation. Introduction. Hermite polynomials were defined by Pius Simon Laplace in 1810 and studied in detail by Pafnaty Chapeshev in 1859. Chapeshev's work was overlooked and they were named later after Charles Hermite, who wrote on the polynomials in 1864, describing them as new. The applications of Hermite equations in physics. Hermite equations and Hermite polynomials are a powerful mathematical tool used in various branches of physics. Their applications range from quantum mechanics, especially in the harmonic oscillator, optics, and electrodynamics, to statistical mechanics, wave equations, and spectral theory. They provide solutions to problems involving oscillatory behavior, Gaussian distributions, and more. Hermite differential equations. The differential equation d squared y by dx squared minus 2x dy by dx plus 2n of y is equal to 0. This is equation y, where n is a constant, is called as a Hermite differential equation. The series solution of the Hermite equation 1 may be expressed as y is equal to summation r varies from 0 to infinity ar x power k plus r. This is equation 2. Differentiate this equation with respect to x. We are getting summation r varies from 0 to infinity ar k plus r into x power k plus r minus 1. Again differentiate this equation 3 with respect to x. D squared y by dx squared is equal to summation r varies from 0 to infinity. This is a constant, therefore ar k plus r. Differentiate this k plus r minus 1 into x power k plus r minus 2. This is equation 4. Substitute this 2, 3, 4 in 1. We are getting, that is in equation 1 is d squared y by dx squared. This is d squared y by dx squared minus 2x dy by dx plus 2n y is equal to 0. This is equation 1. D squared y by dx squared is summation r varies from 0 to infinity ar k plus r into k plus r minus 1 x power k plus r minus 2. Next term is minus 2 x into dy by dx. We know that dy by dx is k plus r into x power k plus r minus 1. But already one x is there. Therefore, this term becomes x power k plus r. This term is 2n y x power k plus r is equal to 0. Again, this equation may be written as r varies from 0 to infinity ar k plus r into k plus r minus 1 x power k plus r minus 2. Coupling these two terms, minus 2ar into x power k plus r, we are taking 2ar into x power k plus r outside. Therefore, we are getting k plus r. This term is minus n. Equating to 0, the coefficient of this equation is an identity, and that is why the coefficients of various powers of x must be 0. Next, we have to setting up of recursion relation, that is equating to 0 the coefficient of lowest powers of x by putting r is equal to 0. Therefore, r is equal to 0. 0, here also 1 0, here 1 0. If we put r is equal to 0 means this k power r minus 2, we are taking only this term. Therefore, this becomes a naught k into k minus 1 is equal to 0. A naught being the first term of the series, that will not be equal to 0. Therefore, either k is equal to 0, or k minus 1 is equal to 0. Therefore, k is equal to 0 or k minus 1 is equal to 0. That is k is equal to 1. Therefore, either k is equal to 0 or k is equal to 1. Again, equating the coefficient of x power k minus 1 by putting r is equal to 1 in this equation. We are getting a1 into k plus 1 into k is equal to 0. Here, since k plus 1 is not equal to 0 for any value of k given by this equation. Therefore, equation 8 implies that either this k is equal to 0 or this a1 is equal to 0 or this both are equal to 0. Now, equating to 0, the coefficient of general term x power k plus r to 0. Therefore, this equation becomes ar plus 2 k plus r plus 2 into k plus r plus 1 minus 2ar into k plus r minus 1 is equal to 0. So, ar plus 2 is equal to, taking this to this side, this becomes 2 into k plus r minus n divided by k plus r plus 2 into k plus r plus 1 into ar. Writing this as 2 into k plus r minus 2n divided by k plus r plus 2 into k plus r plus 1 into ar. Now we have to determine the values of the coefficients. First case, by putting k is equal to 0. We know that ar plus 2 is equal to 2 into k plus r minus 2n divided by k plus r plus 2 into k plus r plus 1 into a of r. In this equation, we have to put k is equal to 0. Therefore, 2r minus 2n divided by r plus 2 into r plus 1 into ar. Putting r is equal to 0, 2, 4, etc. in the equation ar plus 2, that is 2 into r minus n divided by r plus 2 into r plus 1 into ar in this equation. This side ar plus 2. Therefore, putting r is equal to 0 means this term 0. Therefore, minus 2n divided by r0 means 2. Here r0 means 1. Therefore, 2 into 1. r0 here means a naught. Therefore, minus 2n by 2n factorial into a naught. Again, put r is equal to 2. ar plus 2. Therefore, a4. If we are putting r is equal to 2 means 4 minus 2n divided by, this is 2 means 4, this is 3. Therefore, 4 into 3 into a2. Therefore, again substitute a2 from here. From this equation, we are taking, from this part, we are taking minus 2 outside. Therefore, this becomes n minus 2. Already our minus 2 is there. Therefore, 2 into 2, 2 squared n into n minus 2 by 4 into 3 into 2 factorial becomes 4 factorial into a naught. Thus, the general term of the coefficients are given by a2m is equal to minus 2 power m n into n minus 2 up to n minus 2m plus 2 divided by 2m factorial into a naught. This is given by equation 12. Similarly, we are putting r is equal to 135 in that expression. If we are putting r is equal to 1 means this side this is equal to a r plus 2. Therefore 1 means a3. Here 1 means 2 minus 2n divided by 3 2 into a1, taking minus 2 outside, therefore minus 2n minus 1 by 3 factorial into a1. If we are putting r is equal to 3 in this equation, 2 into this 3 minus n, therefore 6 minus 2n divided by 5 into 4 into a3. Again, we have to substitute a3 from here, and from these equations we have taken minus 2 outside, therefore this becomes, this term becomes minus 2 into n minus 3 divided by 5 4 minus 2 into n minus 1 into 3 factorial. Therefore, this becomes minus 2 whole squared n minus 1 n minus 3 by 5 factorial into a1 and so on. In general, this may be written as a2m plus 1 because a3, a5, a6. Therefore, this is a2m plus 1 is equal to minus 2 power m n minus 1 n minus 3 up to n minus 2m plus 1 divided by 2m plus 1 factorial. Into a1. Now we are keeping that a1 is, if a1 is not equal to 0, then we have written from this equation y is equal to equation 1, that is y is equal to summation r varies from 0 to infinity ar x power k plus r. Putting this term k is equal to 0 x power r. Therefore, put r is equal to 0 a naught x power 0 means 1, and if r is equal to 1 means a1 x, r is equal to 2 means a2 x squared plus etc. Now substitute a naught, a1, a2, a3 etc. and splitting a naught, a2, a4 term, taking the for that term a naught outside this equation, and for the second part a1 outside the remaining. This is when a1 is not equal to 0. But in case when a1 is equal to 0, a1 is equal to 0 means this term cancels and remaining will be a naught into 1 minus 2n by 2 factorial into x squared plus 2 squared into n minus 2 by 4 factorial x power 4 plus etc. The last term is minus 2 power m n into n minus 2 up to n minus 2m plus 2 by 2m factorial into x power 2m plus etc. We have to say this as equation y1. Second case, when k is equal to 1, when k is equal to 1, the equation a r plus 2 becomes a 2 into r plus 1 minus 2n divided by r plus 3 into r plus 2 into a of r. Again, substitute r is equal to 135 etc. in the above equations. We get a3 is equal to a5 is equal to a7 is equal to 0 since a1 is equal to 0. Also putting r is equal to 0, 2, 4 etc. in equation 15, we get r is equal to 0 in this equation. A2 is equal to 2 minus 2n divided by the 0 means 3 into 2 into a naught. Taking minus 2 outside, minus 2 into n minus 1 by 3 factorial into a naught. Similarly, for a4, put r is equal to 2. This becomes 2, 3 upper 6 minus 2n divided by 5 into 4 into a2. For a2, substitute here. Therefore, this is equation and taking from this part minus n outside, this becomes minus 2 outside, this becomes n minus 3. Already one minus 2 is there, therefore minus 2 whole squared, n minus 1 into n minus 3 divided by 5, 4 into 3 factorial, that becomes 5, 4, 5 into 4 into 3 into 2 into 1, that becomes 5 factorial into a1. Like this, we have to write the general term. A2m is equal to minus 2 power m, n minus 1, n minus 3 up to n minus 2m plus 1 divided by 2m plus 1 factorial into a naught. Therefore, the general term we know that y is equal to summation r varies from 0 to infinity ar x power k plus r. Now we have to put in k is equal to 1. Therefore, this becomes ar x power r plus 1. This can be written as expanding r is equal to 0, 1, 2, 3, 4, 5, etc. Since a1 is equal to a3 is equal to a5 is equal to 0, we are getting only a naught x plus a2 x cube plus a4 x power 5 plus etc. Substituting for these values a2, a4 etc. and taking a naught outside, we are getting x minus 2 into n minus 1 by 3 factorial into x cube plus minus 2 whole squared n minus 1 n minus 3 by 5 factorial into x power 5 plus etc. The last term is minus 2 power m n minus 1 n minus 3 up to n minus 2m plus 1 divided by 2m plus 1 factorial into x power 2m plus 1 plus etc. This can be written as y2. We have to say this is as y2. Therefore, inspection of 13, 16, and 16 so that 16 is a part of the second part of 13 except that a0 is replaced by a1 and hence in order that the Hermite equation will have two independent solutions, a1 must be 0, must have the equations 14. In view of this, the general solution of the Hermite equation is given by y is equal to ay1 plus by2. This is equation 17 where a and b are arbitrary constants and y1, y2 are given by equations 14 and 16.